Physics is all about making predictions. Given enough data about some system at a snapshot in time, we can use the relevant equations for motion to predict what that system will look like at some point in the future, or rewind time and see what it used to look like in the past. We call this an initial value problem. They pop up everywhere in physics. In general relativity though, the notion of a snapshot in time gets thrown out the window, so we have to replace it with what's called a Cauchy surface. This is some space-like or null surface across space-time which all trajectories of light and matter pass through. So given enough data on this Cauchy surface, it lets us set up an initial value problem. How do we define a Cauchy surface for a black hole space-time? The easy answer is to define one before the black hole forms. This lets us predict the future perfectly well. Things become tricky, however, when we want to retrodict the past using only data from after the black hole's formation. We can't define a Cauchy surface entirely outside of the black hole's event horizon. There wouldn't be enough data. This is due to no-hair theorems. Hairs are the properties of black holes that we can use to tell them apart. For general relativity coupled to the standard model, we only need to know about the mass, angular momentum and electric charge to be able to fully describe a black hole. Clearly just 3 parameters alone can't be enough to tell us about everything that went into the black hole. The information we need can't have been destroyed though. This is because quantum systems evolve unitarily. The amount of information required for a full description is the same at any point in time. So if information can't be destroyed, it must be hidden from us. Nothing escapes a black hole, so the information must be locked away forever behind the event horizon. So far we have a nice consistent theory, but in the 1970s Hawking came along and broke it. He showed that massless particles are produced around the black hole's surface in a random process called Hawking radiation. Over time, the black hole radiates away its mass until eventually it disappears entirely, leaving only the vacuum. So, where did all of the information go? This question is the information paradox, and it's caused physicists many sleepless nights. And it really is a paradox. Once we assemble our axioms, we see that they're not consistent with each other. The only way to solve it is to find the false assumptions we made along the way. There have been several claims to have solved the information paradox, each of them challenging a different set of assumptions and then showing that a mathematically consistent theory is possible. In the absence of direct experimental evidence, however, which is very difficult to do for black holes, the validity of these solutions comes down to the strength of the arguments for which assumptions can and can't be relaxed. For the rest of the video, I want to talk about one such approach to the paradox that Hawking himself chose to work on in his later years. It comes from looking at infrared equivalences, that is, the similarities between different parts of physics as the energies involved drop to zero. Recent work in this area has found 2 flaws with the original formulation of the paradox. These false assumptions are as follows. The first is the statement that black holes have no hair, and the second is that there is nowhere for information to be stored after the black hole disappears. So if black holes are actually hairy, then what's wrong with the no-hair theorem? Surprisingly, nothing, other than its name. You see, no-hair theorems are possibly the worst named theorems in all of science. They do not say that black holes have no hair. Everyone agrees that black holes have hair. The mass of the black hole is hair. We can tell 2 black holes apart if they have different masses, and it tells us something about how they were formed. Perhaps we should call them not enough hair theorems, but even then this might not be fully accurate, as we shall soon see. What do no-hair theorems actually say then? First of all, we can only talk about a no-hair theorem. The no-hair theorem we choose depends completely on what physical theory that we're working with. For instance, when we couple electromagnetism to general relativity, we get an extra hair because the black hole can now possess an electric charge. We could even move beyond the standard model and take a theory in which magnetic monopoles exist. This would give us even more hair because the black hole can now have a magnetic charge. The mathematical statement of a no-hair theorem is that all stationary black hole solutions to our theory are diffeomorphically isometric to Kerr-Newman spacetimes. That's quite a mouthful, so you see the need for a punchy name. Essentially what this is saying is that for any good stationary black hole spacetime, we can find a smooth map which takes us to another specific spacetime called a Kerr-Newman spacetime. And we can also find a smooth inverse to that map which takes us back again. The details of the Kerr-Newman spacetime aren't important, but it's described by a metric with only a handful of parameters. These few parameters are the few hairs of the not enough hair theorem, and so we see where the traditional interpretation comes from. Punchy names such as no hair theorem or not enough hair theorem do convey the main takeaway of the theory, but they miss out on the subtleties involved in its formal definition. It is through these subtleties that it was found that black holes could have a hairdo of soft hair, a possibly infinite amount in fact, which suddenly stops becoming so insignificant that we can still dismiss it as basically no hair. A hair is a type of conserved quantity or charge, and soft means that we've taken its energy to zero. Charges are conserved whenever there is a symmetry of nature. For momentum, the symmetry is translation. For angular momentum, the symmetry is rotation. And for soft hairs, the symmetry is some kind of supertranslation or superrotation. You likely haven't heard of these, but they come from considering the physics at the asymptotic boundaries of a spacetime. This is the mathematical limit of taking points infinitely far away. In special relativity, we only have three types of symmetry: translations, rotations, and boosts. Putting these together, we have a 10-dimensional symmetry group that we call the Poincare group. But when we move to general relativity, we have to upgrade this symmetry group to include our new supertranslational and superrotational symmetries. Our new symmetry group is called the BMS group, and it is infinite dimensional. This is a very surprising result. For asymptotically flat spacetimes, meaning flat at the edges, you'd think that the symmetry group would just be the Poincare group again, but weirdly this isn't true. And with an infinite number of symmetries, this means that there must be an infinite number of conserved charges. Let's say all that another way. If we boost a black hole, we change its energy and momentum so the quantum state is different. Two black hole spacetimes are not physically equivalent if they differ by a boost. But boosts are elements of the Poincare group. Our upgraded BMS group doesn't have a preferred element specifically for boosts. Any BMS translation is just as good. And with an infinite number of BMS translations, there are an infinite number of ways to tell two otherwise identical black holes apart. These conserved supertranslation and superrotation charges have two consequences. The first is that Hawking radiation can carry these charges, and so the quantum state of these particles may be correlated to the quantum state of the black hole. The information paradox incorrectly assumes that these correlations don't exist, and so it misses out on a possible way for information to escape. The second consequence is that the vacuum itself can have these charges. The information paradox assumes that the vacuum is unique, but these BMS charges, or soft hairs, have no associated energy. This means that the empty space left behind after a black hole has evaporated can possess different configurations of BMS charges, which may be correlated to the quantum state of the black hole. This provides somewhere for information to be stored after the black hole has vanished. We've now arrived at two ways to rescue information out of a black hole. Does this solve the information paradox? Well, we're not sure yet. An important caveat to the infinity of soft hair that a black hole can have is that it doesn't really make sense to talk about soft hair that's localized to a region smaller than the Planck length. This gives us a lower bound of soft hair and means that, while there's still a lot of it, there might only be a finite amount and we're not sure if it's enough. we also don't yet fully understand the correlations between a black hole's soft hairdo and the quantum state of the objects which form the black hole. For all we know, throwing two different objects down a black hole could rearrange the soft hair in the exact same way, and then we're seemingly back to square one, unable to retrodict the past. Nevertheless, it's a fascinating angle of attack on the information paradox, and there's every reason to be optimistic.